Hello, in this video we're going to maximize output from a $1,200 production budget where the wage is $20 and the price of capital is $10. Here's our production function, so we're going to try to maximize Q subject to the fact that we only have $1,200 to spend on producing Q and we face these market input prices. Setting up the cost constraint or the cost equation, we have $1,200 to spend. The price of labor is $20 times units of labor, and that's going to be added to the price of capital times units of capital. So that's our cost constraint. Setting up the Lagrangian. The Lagrangian equals the Cobb-Douglas production function plus lambda times the cost constraint. The minus 20L and minus 10K are coming from the fact that I'm moving everything over here on the right-hand side to the left-hand side. So I subtracted 20L from both sides and subtracted 10K from both sides. Taking a partial derivative of the Lagrangian with respect to labor, we get the following result. This 1/3 comes from the exponent on L that I brought down in front, and then L raised to the 1/3 minus 1 gives us L raised to the minus 2/3 power. Lambda multiplied by minus 20L, the partial derivative of that will just be minus 20 lambda. I don't have to worry about lambda times 1200 or lambda multiplied by minus 10K. Neither of those terms have an L in it, so they're just going to be treated as a zero or a constant when we take a partial derivative. The next partial derivative is the partial derivative of the Lagrangian with respect to capital. The 2/3 here on the K term gets brought down in front. 2/3 minus 1 leaves us K raised to the minus 1/3 power. And then lambda multiplied by minus 10K, the partial derivative of that is just minus 10 lambda. And one more partial derivative. We will take the partial derivative of the Lagrangian with respect to lambda. We'll get back what is in the parentheses here, the cost constraint. All these partial derivatives are set equal to 0. The next step is we are going to solve our first two partial derivatives for lambda. So we're going to take this partial derivative result and solve it for lambda, moving 20 lambda over to the right-hand side and then dividing through by 20. We will get this result. And then this next partial derivative, we'll do the same thing, moving 10 lambda over to the right-hand side and dividing through by 10. We'll get this result. I'm going to set both of these lambda equations equal to each other. So this is what we found on the last slide, setting lambda equal to lambda, and now simplifying. The first thing I did was I multiplied both sides through by 60. So 60 times 2 is 120. Divided by 30 gives us 4. Following the rules of exponents, on the left-hand side, we're going to move this L to the minus 2/3 into the denominator, and that will then become L raised to the 2/3 power. And we'll do a similar thing on the right-hand side. K raised to the minus 1/3 power is the same thing as 1 over K to the 1/3. Next, we will multiply both sides through by L to the 2/3. So L to the 2/3 times L to the 1/3 is just L. And then we're going to do a similar thing with the K term, multiplying both sides through by K to the 1/3. K to the 1/3 times K to the 2/3 is just K. So we got this key result that K equals 4 times L. Plug that into the cost constraint. Here it is once again. Where I have K, I'll plug in 4L. So 1200 equals 60L. Dividing through by 60. L equals 20. And since K equals 4 times L, K will equal 4 times 20 or 80. So that is our optimal input mix. Using 20 units of labor and 80 units of capital will give us the maximum output given that we only have $1,200 to spend on production. Okay, I hope you found this video helpful.